Am I audible to all of you? So, let's start this session. So, I welcome you to all to this Power System Engineering tutorial session. And this session will be taken up by me, Mohammad Owais Khan, the Prime Minister Research Fellow from the Department of Electrical Engineering, EMU. I hope you have gone through the uh, lecture on NPTL, like how we because in this week we are talking about transients in power system. I assume that you have all gone through the derivation, how we are going to derive various equations regarding the voltages, reflection, and voltage. You know how the transients in the simple circuit can be uh, modeled. So I hope you have gone all through to those equations and derivation. But still, I will just give you know uh, a brief overview. Then we will solve some questions because in this topic the questions are very important. Numericals. So, what is a transient? What is a transient? First, we should know about it. Okay. So actually, it is a phenomena. It is a phenomena which is independent of time, or I would say a periodic of time, a periodic of time, and it is an instantaneous phenomena. It is, I would say, short duration phenomenon. Okay, so this is the you know, and it's I would say duration. It's a short duration phenomena, like it lasts. It means it lasts for a smaller time as compared to the operating time of system. Okay, but it is it is quite severe. But it is quite severe. Okay, so generally, generally, it has effect on the insulation. It does. It also you know, actually, what happens in the insulation that when it affects the insulation, the heating effects occur. Heating effects occur. So what does it do? Because it breaks down the insulation, which keeps in, which keeps in heating up the equipment. So when insulation break down, the equipment gets heats up, and it leads to the malfunctioning. It also increases the hysteresis losses, because which lead to more current injection. Okay. And the life of the equipment gets short. So these are some of the, you know, I would say, effects of the transient. Okay, so transient, why do transient occurs? Transient occurs when there is an energy storage element like I'm sorry, L or C. Okay, so transient generally occur in the RLC circuits because one time at one point of time energy is stored in some L, then it transferred toward the other. So this change of energy leads to the transients. Okay, and sometimes the fault occurs. So this change of energy leads to the shoot up in uh, the operating values like current or voltages at any point of time. Okay, and I assume that you have gone through the lectures because there are various derivations, and based on that derivation, we will be solving some equations. So, for some numericals. So, I am not going to derive those because you have already gone through the lectures on the NPTL. So, what I will do here, I will, solve some questions, and based on that questions, we will analyze or understand the problems. Okay, so let me see what should be what type of problems we should solve over here. Okay, okay. So one topic is also there, which is traveling waves in the transmission line. Okay, so basically, what happens here is that because the LCR are uniformly distributed over the line, the steady operations could be. The thing is that whenever we talked about steady state operations, we generally talked about using lumped parameters. Okay, lumped parameters. But if we want to, analyze the transient behavior, if we analyze the transient behavior, then these lumped parameters cannot be used. We use distributed parameters, means the actual circuit is how the actual circuit is there. We cannot lump the parameters in the circuit. So therefore, Therefore, for the understanding of the transient phenomena, what we do here, we uses the distributed parameters. Okay, and there is a term which you have gone through in the lectures, which is surge impedance loading, or I would say surge impedance of a line. Okay, it is actually defined as a it is defined as the natural, or I would say it is defined as a natural impedance of the transmission line. Impedance of the transmission line. This characterizes the transmission line. It is also known as the characteristic impedance of a transmission line, and its value is 400 ohms for an overhead transmission line and out 40 ohms for cables. Okay, so it is generally calculated by Z is equal to V by I, which is also known as L by C. Okay, so what happens here is that when these waves, let's say this is a transmission line, and when these waves travel on this transmission line, what will happen if they are at the end of their transmission line, there is no connection, or I would say open end line. What happens if this line is short circuited? Means short circuited line. What will be the behavior? And another is, if there is a resistance connected to this line, so what will be the behavior of the waves when it is terminated by a resistance? Okay, and there are various questions on this, like what happens when it is connected by a cable. Okay, so just a second. Now, for example, first case we will take when it is an open end line. Open end line. So what happens here is that, let's take a circuit here. This is the V, and it is a switch, and it is connected to a, and it is open ended. Okay, open ended line. Okay, so when switch S is closed, the voltage and the current wave will travel towards the open end. These waves are represented by the equation Z is equal to V by I, where we know Z is the characteristic impedance. Now what happened here is that, let's take a last element, a smaller element dx. Now what happens here is that when wave reaches at this point, because the impedance is different here, because there is no impedance, means for an open-ended line, the impedance is infinite. So what it will appear, it will going to see a change in impedance as impedance from Z to infinite. So what will happen here is that the electromagnetic energy stored be like the electromagnetic energy stored by element dx कितनी होगी? It is half L dx I square. Okay, and for the same element, the electrostatic energies, the electrostatic energy in the element is half C dx square V square, because I have already told you we are going to take the distributed parameters in a transmission line. So, since the current at the open end is zero, because it is open-ended, infinite impedance is there, the electromagnetic energy vanishes. ये जो I ये जो energy है ये वाली, it will get vanished because it is an open-ended element, but it will vanish and transform into a electrostatic energy, which means half L dx I square is equal to half C dx V square. Okay, and we would change this voltage into, let's say, small e, because the voltages and I will change. So let the e be the change in the voltage at the end. Let's take this. So if we go on and rearrange this, it will come out to be C by L, because this dx will cancel out, this will cancel out here, and if we rearrange this like that, it will come out to this, and it will be equal to how much? And we also know E is equal to Iz, okay, which is equal to V. So what happens here is that the change in voltage is V. So what happens is here that the potential, which is E, at the end of at the open end will be raised by V. Okay. Therefore, the total potential, because the another potential is V, but the change in potential is V, so the total potential at that end will be total potential of the open end when the wave reaches is V plus V, which is equal to 2V. Okay. So here, what at that point it becomes 2. So now what happens here is that, as we have told you about, the wave will start traveling when the switch is closed. Okay, so these waves are known as, which are traveling toward the open end, are known as incident waves. And after the wave reaches at the end point, there is a rise in potential there due to the wave, which is reflected at the open end, and actual voltage will be considered as, like, the refracted wave voltage, I will write it over here, is equal to इंसिडेंट वेव, जो वेव इस साइड से ट्रेवल करके जा रही है, प्लस रिफ्लेक्टेड वेव. ओके, so this is how we going to calculate this. Okay, as soon as the incident current reaches, that I की जो wave, when it reaches toward the end, the current at the open end becomes zero. यहाँ पे करंट कितना हो जा रहा है, zero, because I have just told you that all the electrostatic energy will be converted toward the electromagnetic energy will be converted into electrostatic energy. So if that the current at that open end becomes zero, how can we say that this could be explained? Like it could be explained like एक wave इधर से जा रही है, यहाँ पे एक zero हो जा रहा है. It will only be possible when there is another wave which is reflected and it is coming in a negative value. Okay, so with a negative sign and coefficient, then only at that point I is zero. I will show over here how this phenomena goes on. So let's see, let's take this is a voltage. This is a voltage wave. It will allow to, okay. Then this wave is current. Okay. This is a current wave and this is a voltage wave. And it is a magnitude V. So what we have told over here is that when it reaches the point at open end, its magnitude becomes V. So the total magnitude, the potential at the open end will be 2V. So what it will do here, it get reflected by a voltage of 2V. Okay, get it? But for the current, we have been told that the current at the open end becomes zero. It can only be zero when there is another wave which is traveling in a negative fashion and its magnitude will be equal to -1. Then only it can, then only it can give the equivalent at that point 0, because +1 it will go here, -1 is here, then at that point what will happen, I become 0. But here what is going to happen here is that V is going over here, then there is V is coming also here, then it will become 2V. Okay, V minus V, it become 2V. Okay, like this. So it shows that it shows that how we going to say, this shows the variation of voltage and current in the voltage and current in the open-ended line. Okay, we will solve some question over there just a minute back after. Then for example, there is another case when it is short circuited. When it is short circuited, just a second. When it is short circuited, so what happens here is that when the line is short circuited, like it is this, okay, and it is then short circuited like this. Okay, this is voltage, this is like switch. Okay, when it is short circuited, so the voltage at the point of end of line becomes 0, and the current will be reflected then current at the point become I. So it will be reflected by a 2I value. Okay, this is how we are going to solve it. Okay, let's say this is line is connected with a cable. Okay, line is connected with a cable. At the end of the transmission line, there is a cable connected, Z2 and Z1. So the reflected voltage will be calculated. तो इसमें क्या होता है, जब केबल से कनेक्ट होता है तो इसके अंदर रिफ्लेक्शन एंड रिफ्रैक्शन, कुछ पार्ट of the voltage will come back, but some part of the voltage will be refracted toward the Z2 or toward the cable. Okay, तो refracted voltage कितने होंगे इसके अंदर, refracted voltage will be 2 times Z2 divided by Z1 plus Z2 into V. Okay, voltage at that point. ठीक है, तो we will solve some questions regarding this and you have to give me the answer. So first question, because in this topic, theoretical you can learn at any time, because there are lectures over there, but it's very important to solve the question because in exam the questions will be taken up. A surge of 15 kV volt magnitude travels along a cable towards its junction with an overhead line. The the index the inductance and the capacitance of the cable and overhead line are zero point 0.3 millihenry and 0.3 millihenry and zero point 0.4 microfarad and 1.5 millihenry and 0.012 microfarad per kilometer. Find the voltage rise at the junction due to surge. So option A is 25 to 26 kV, B is 24 to 25 kV, C is 27 to 28 kV, and D is none of the above. Okay, so you can try to solve it. तो इसमें क्या कहा गया है कि It has been said that a surge of 15 kV magnitude travels along a cable towards its junction with an overhead line. The inductance and capacitance of cable. तो इसके अंदर inductance and capacitance of cable क्या है? L है 0.3 मिली हेनरी and capacitance है 0.4 माइक्रो फैराड. And for overhead line, L is 1.5 millihenry and C is 0.012 microfarad per kilometer. अब इस In this problem, the surge is traveling from the cable toward the overhead junction. Okay, so let's say this is overhead line and this is cable, and a surge is traveling like this. So we have to find the voltage rise at this junction. So before that, we will calculate the surge impedance, or we would say surge impedance of cable. It will be under root L by C. It is equal to, what is L? 0.3 into 10 raised to the power minus 3 divided by zero point 0.4 into 10 raised to the power minus 6. Then it will come out, if we rearrange this, it will come out to be 3 into 10 raised to the power minus 4, then 4 into 10 raised to the power minus 6, 7. And if we solve it, it will come out to be 27.38. So this is the surge impedance of a cable. Now, natural impedance or the surge impedance of line is also under root L by C. So what is L? 1.5 into 10 raised to the power minus 3 and 0.12 into 10 raised to the power minus 7. If we solve it, it will come out to be 353 ohms. Okay, so we should know the formula. The voltage rise at the junction is the voltage transmitted into a overhead line as the voltage is zero before the surge reaches the junction. तो यहाँ से जो सर्ज जा रही है इसकी वजह से जो वोल्टेज जंक्शन पे राइज होगा वो हमें निकालना है. And what it is? It is the, let's say this is E double dash. We know that 2 into 353 and multiplied by 353 plus 27. It is multiplied by the surge of the voltage, which is 15 kV. We should know the formula. E double dash is equal to 2Z2 divided by Z1 plus Z2 into V. These are formulas you should remember, because if you don't remember these formula, you can't solve it. So if we solve it, it comes out to be 30 into 353 divided by 353 plus 27. It will be 30 into 353 divided by 380. So it will come out to be 27.88 kV. So the voltage rise at the junction is equal to the 27.88 kV. So based on that, the correct answer will be this is the C is the correct answer. Okay. If you have any query, you can ask in the chat box. Okay. So we will solve another question. Question number 2. And I need you to answer them in the chat box. So what is the question? A surge of 100 kV traveling in a line of natural impedance 600 ohm, and it arrives at a junction with two line impedance of 800 and 200 ohm respectively. Okay, we have to find the surge voltages and current which is transmitted into each branch line. Okay, so what happens here is that it is like a cable. Okay, so what happens here is that the natural impedances of Z1 is 600 ohm, let's denote with 1, and Z2 is 800 ohm, and Z3 is equal to 200 ohm. Okay, so it is like Z1 is here, Z2 and Z3. Okay, the surge magnitude V surge is 100 kV. So what happens here is that when the surge reaches a joint, it will suffer reflection. Okay, and it will travel in the transmitted voltage will travel. So we should know the formula of how to calculate the transmitted voltages for the two surges. To how we can calculate the transmitted voltage when a surge is divided into two lines like a T joint. So you should know the formula. Just a second. Transmitted voltage. How we can calculate? Let's say this is E. It is 2 V by Z1, 1 plus Z1 plus 1 by Z2 plus 1 by Z3. Okay, this is how we are going to calculate. So here, what is the surge? V is the surge. So 2 into 100 divided by, what is Z1? Z1 is 600, and 1 by 600 plus 1 by 800 plus 1 by 200. So it will solve it out like this: 1 by 3 divided by, and using the calculator we will calculate these values. It will come out to be 1.67 plus 1.25 plus 1 point, sorry, this is zero point 0.5. Just a second, I will write it down over here. It will be equal to 0.33, 1 by 3, 1.67 plus 1.25 plus 5 into 10 raised to the power minus 3. So if we solve it, it will come out to be 33.7.92 into 10, and it is equal to 40.04 kV. Okay, so the transmitted voltages in both these will be 42 here and 42 here. Now we have to calculate the transmitted current, because in the question it has been asked to do. So the transmitted current, transmitted current in line Z2 is. But the thing is here is that voltage is transmitted will be same for these both lines, but the current will be different because they have a different surge impedance. So Z2 is equal to, what is the transmitted voltage? Let's say VTR, and it is divided by how much? 800. For Z2 is 800. Okay, so what is VTR? 42.04 into 1000 divided by 800, because we have to change into voltage, and it will come out to be 52.55 ampere. Okay, so transmitted current in line Z2 क्या होगा? It is 52.55 amps. Okay, now similarly we have to calculate in Z3. So the transmitted so the transmitted current in line Z3 will be, क्या होगा? It is 42.04, because the voltage transmitted is same, but the impedances is different, and it will come out to be 210.2 amps. So we can finally say the transmitted current in line Z3 will be 210 on 210.2 amps. So this is how we should calculate all the numericals. Like before solving these numerical, we should know what type of formula we are going to use. These formulas are very much important. Okay. Now, if you have any question, you can ask in the chat box. Okay. So moving on towards other question. Just a second. Question number 3. So the question here is that the reflection, the reflection coefficient of voltage, let's say it is rho v, and the current, let's say it is rho t, at the load end of an open circuit open circuited line open circuited line R. So there are various options. First is rho v is 0 and rho t is 2. B, rho v is minus 1 and rho t is 1. C, rho v is 1 and rho t is minus 1. D, rho v is 2 and rho t is 0. So this is how we are, this is the question. So now tell me the correct answer if you know. Okay. So we have just discussed about the operation of this open circuited line. So what is in the open circuit line? What happens? Let's say this is a voltage V and it is connected through a switch. Okay, yeah. Okay. Let me solve it for others also. Then it is connected to the switch. It is C. So it is an open circuited line. So here, let's say this is ZL. It will tends to, it will have a value of infinity. So now we should know, and the value of the impedance, let's assume it is Z of the line. So we should know two formula. First one is the reflection coefficient of voltage. How we going to calculate? Rho v is equal to ZL minus ZC divided by ZL plus ZC. So let's rearrange this like 1 minus ZC by ZL divided by 1 plus ZC by ZL, and ZL cancel out. Okay. Now we know that if ZL here, ZL is infinity. So if ZL is infinity, then whole terms will become 0. So this whole terms will become 0. So the reflection coefficient rho v will comes out to be 1. Okay. Now for B means reflection coefficient of current. It is let's say this is rho t. It is calculated by this formula Zc minus ZL divided by Zc plus ZL. Doing similar things by rho t is equal to ZL by ZL. So Zc by ZL minus 1 divided by Zc plus ZL plus 1. If ZL tends to infinity, this whole terms will become 0. This whole terms will goes towards the 0. So it will come out to be rho t is equal to minus 1. So the reflection coefficient rho v is 1 and rho t, which is current coefficient, is minus 1 for a open circuited line. And this I have already shown you in starting that for open circuited line at the junction here, it becomes current becomes 0. So how it becomes 0? ये कब 0 हो पाएगा? It only can become 0 when the incident wave of current having the magnitude 1 gets superimposed with another wave whose which has a magnitude of minus 1. Then only can, if we calculate the equivalent here, it will become 0. So this shows that whatever we have discussed is correct. Now another thing is here, I have shown you that one voltage wave is going here, and at that point the change in voltage is V. So a change in voltage is V means another wave will go here with a positive magnitude, then both these get superimposed and 2V will get like this. So this shows that the reflection coefficient is 1. So basically, if we go toward the answer, I think C is the correct answer. Yes, C is the correct answer. Okay. So now question number 4. Which of the following statement is correct when a transmission line is terminated in an impedance greater than the its characteristic impedance? Okay, so we have to give the correct answer. A. The traveling the traveling voltage wave is reflected back is negative and the current wave reflected is positive. Okay. B is traveling voltage wave is positive and the reflected current wave is negative. Okay. C. Both waves are positive. D. Both are negative. If you know the answer, you can write in chat box. Otherwise, I will solve it for you. Okay, let's solve this. So we just know the reflection coefficient formula. Rho v is equal to 1 minus zc by zl plus 1 zc by zl. Okay. In this, it is given zl is greater than zc. What is zl? It is the terminating impedance. Okay. So it is given in this question if the line is terminating into a impedance which is greater than its characteristic impedance. So what will happen here is that it is ZC is less than ZL. So ZC by ZL will be less than 1. Okay. So this value will become positive. So rho V will become positive. Okay. Why? Because ZL is greater than ZC. So whole numerator will be less than 1 and then it will become positive. Okay. Now for similarly for current reflection, rho t is equal to, we just have zc by zl minus 1 divided by zc by zl plus 1. So zc by zl is already less than 1. If we subtract 1 from that, it will become negative. Okay. So we can say that rho t should be less than 0. So it is rho t and rho v. If we go towards that, we can say that what is the correct answer? Traveling voltage wave is positive, reflected wave is negative, so B is the correct option. Okay. Now, next question, question number 5. A three-phase 440 kV and 50 Hz 250 km long lossless transmission line has lossless transmission line has line inductance of 2.95 millihenry per kilometer and 0.0345 microfarad per kilometer. If the receiving end of this line is open, find the total surge power. Solve it and write the value of the surge power in the chat box. I'm waiting for you. The first option is 694 to 698. Second option is 678 to 682. Okay. D is 635 to 639 and C is 660 to 664. We have to calculate in megawatt. I'll give you a minute, then you write the answer in the chat box. Then we will discuss it. Okay, let's solve this. So the surge power is calculated by V square by ZC by using the surge impedance. So basically here L is given 2.95 millihenry per kilometer. C is 0.0345 microfarad per kilometer. So if we calculate Z, L by C, 2.95 into 10 raised to the power minus 3 divided by 0.0345 into 10 raised to the power minus 6, it will come out to be 292.4 ohms. Okay. Now for calculation of surge power, it is V square and voltage is given 440 square divided by 292.4 and its value I think will be coming out to be, let me use the calculator. Its value is 662.07 megawatt. Okay, so basically the correct answer here, which one? 662. So it comes in the range of this. So 660 minus 662, 664. The fourth option is the correct option. Okay. Now next question. Question number 6. Okay. A lossless transmission line having surge impedance of 350 ohm is terminated by a resistance of 250 ohm if the magnitude of forward traveling voltage and current are 4.2 kV and 12 ampere respectively. Determine the magnitude determine the magnitude of backward traveling current wave. So basically in this we have been given ZL is equal to 250 ohm and ZC, it is the correct, the surge impedance is 350. If the magnitude of the forward traveling voltage is, what is the magnitude of the forward traveling voltage and current is, IF is equal to 12 ampere. So we have to mm, no, not 700, not this one. I will solve it for you. So the magnitude of the traveling wave, backward traveling wave, will be how much it will be. We have to calculate it, okay? Because it is terminated by a resistance, okay? So mm, it will be like this, okay? Just a second, magnitude. I will write it down for you. VB is IB. Yes, 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 yes. It's correct. Now it's correct. So IB is equal to how much? 350 minus 250 divided by 350 plus 250 into IF. So if we calculate this is 100 by 6 700. Okay, how much it is? It will be into 12 divided by 600. So it will come out to be 2 ampere. Okay, so we will use this. So basically, I have not given the option, but the answer is 2 ampere. Okay, backward it is, so mine it will be 2 ampere. Okay, now the next question here, what we are going to solve is question number 6, 7. Okay, a lossless transmission line having surge impedance of 150 ohm is terminated by load resistance of 200 ohm. Okay, 200 ohm. The if the magnitude of forward if the magnitude of the forward traveling voltage is 5.6 kV, calculate the current flowing in amperes through the load. So there are options. A is 24, B is 28, C is 32, and D is 20. So I will wait for a minute and you give the answer in the chat box. So what we will do here, first we will calculate the reflection coefficient. The reflection coefficient of voltage. We know rho v is equal to ZL minus ZC divided by ZL plus ZC. So what is ZL? 200 minus ZC 150. 200 plus 150. So it will come out to be 50 divided by 350, it is 0.142. Okay, 0.142. I think, let me check. I have to check it. Yes, 0.143 exactly. Let me. Okay. So the reflected voltage towards the line, the reflected voltage towards the line will be 0.143 into 5.6. So if we multiply it by 5.6, it come out to be zero point 0.8 kV. Okay, we can use this. Now, voltage across the load resistance, load at the end of the line. Just a second. A lossless, the magnitude is this. How much it is? The magnitude of the forward traveling voltage is 5.6. So the voltage toward the load end of the line will be the sum of these 5.6 plus zero point 0.8. So it will be equal to 6.4 kV. So the current flowing through the resistance will be 6.4 kV divided by the impedance, oh sorry, resistance of the load. It will 200. Okay. So it will be 6400 divided by 200 and it will come out to be 32 ampere. So we can see that the correct answer will be C, 32 ampere. Let me insert more slides. Okay, so now next question we are going to solve. Question number 8. An overhead line with a surge impedance of 400 ohm is connected to a transformer by a short length of cable of surge impedance of 100 ohm. If a rectangular wave surge of 50 kV travels along the line towards cable, the voltage of traveling wave from junction of overhead line towards cable towards the transformer through cable will be. So A is 30, B is 20, C is 50, and D is 25. So give me the correct answer in the chat box. So let me solve it for you. Reflection coefficient of voltage traveling from junction of overhead line towards cable will be, let's say, rho v. So ZC minus Z line divided by Z, let's say cable, let me write cable plus Z overhead line. So what is cable impedance? The cable impedance here is how much? It is 400. No, no, yes. Okay. No. Overhead has a 400, but the cable impedance is 100. This is the cable impedance and this is overhead impedance. Okay. So how it is 400? It will be 100 minus 400 divided by 100 plus 400. So it will be minus 300 divided by 500 and will come out to be minus zero point 0.6. Now the reflected voltage towards OHL is VR is equal to minus no, rho V into V, which is minus zero point 0.6 into 50. It will come out to be minus 30 kV. Therefore, the wave of voltage traveling from junction of OHL to the cable would be V1 plus VR. It is 50 plus minus 30 is equal to 20 kV. So this is the answer. So therefore the correct is B, 20 kV. I hope you understood that. Now next question is question number 9. Okay. So in this question it is given an overhead line having impedance and capacitance of 1.35 millihenry per kilometer and 0.08 microfarad per kilometer is connected in series with an underground cable having inductance and capacitance of 0.24 millihenry per kilometer and 0.32 microfarad per kilometer. We have to calculate the approximate surge voltage which is reflected back which is reflected back into the line due to a surge of 120 kV traveling towards junction from sending end of OHL. So the options are minus 64.5, A minus 64.5, B 64.5, C minus 78.2, and D minus plus 78.2. Okay, so you have to give the correct answer. In this question, it is given an overhead line which has an impedance of this much is connected in series with an underground cable which has a impedance of this much. Okay, we have to calculate the approximate surge voltage which is reflected into the line due to the surge of 120 kV traveling towards the junction from the sending end of a OH. So what we are going to do here, we have to calculate first the ZOH. It is equal to 1.35 into 10 raised to the power minus 3 divided by 0.08 into 10 raised to the power minus 6. It will come out to be, if you use the calculator, it will come out to be around 129.9 ohm. Similarly, for Z cable, we have to calculate 0.24 into 10 raised to the power minus 3, then 0.32 into 10 raised to the power minus 6. It will come out to be 27.4 ohm. Okay, then we will calculate the reflection coefficient of reflection, rho v. It is equal to Z cable minus Z OHL divided by Z cable plus ZOHL. So rho V will be equal to Z cable we know 27.4 minus OHL 129.9 divided by 27.4 minus plus 129.9. So if we solve it using calculator, it will come out to be minus 0.65. No, no. Yes, yes. It is minus 0.65. So reflected voltage towards OHL, how much it will be? VR is equal to simple formula into V1. सर्ज कितने की है? सर्ज है 120 की. रो भी कितना है? 0.6518. So it will come out to be minus 78.2 approximately. So the correct option will be the correct option will be minus 78.2. Okay. So we will solve another question. Hope you have understood that. Question number 10. Just a second. Okay. An 132 kV three phase long loss line transmission lines has the line impedance of 3.65 millihenry per kilometer. If the receiving end of this line is open and the distance traveled by a surge of 15 microsecond is 1.4 kilometer. Calculate the characteristic impedance. These are the options. So give me the correct answer. Okay. You should know the various formulas like electrical length or beta. These are the formulas you should remember. So these questions are simple, but if you don't remember the formulas, then it will be difficult. Like beta is equal to 2 pi by lambda. Okay, and various things. So let me solve it for you. Okay, so the electrical length we have to first calculate. it will be equal to beta LC. What we have to calculate here, first of all, sorry, just a second. I wrote the wrong question. Okay, just a second. And the question is here 132 kV 3 4 has line impedance is this. Okay, yes. So we have to calculate the surge impedance. Calculate the characteristic impedance. So what is the characteristic impedance? We should know that Vp is equal to 1 under root LC. Okay. Uh, Line impedance is this, receiving end is open, distance traveled by the surge is okay. So Vp is equal to 1 by under root LC. We know that the wave velocity. Okay. Here in this question it is given the distance traveled by the surge of 15 seconds is 1.4 kilometer. So wave velocity multiplied by the time it is equal to distance, which is 1.4 kilometer. And here t is 15 microsecond. So Vp will be equal to how much? So Vp is equal to how much? Uh, it is equal to 1.4 divided by t. 1.4 divided by 15 into 10 raised to the power minus 9 into 10 raised to the power 3. So it will come out to be 9.33 10 raised to the power 4. If we convert back into kilometer, then kilometer per second. Okay. So this is the Vp, which is the wave velocity. But we also know the wave velocity is 1 upon under root LC. So it is equal to 9.33 into 10 raised to the power 4. So why are we doing this? Because we have to calculate the surge impedance, sorry, the characteristic impedance. And for that we should know the value of L and C. But here in the question we all only know the value of line of L. But we have to calculate the value of C also. Then only we can estimate the surge impedance or the characteristic impedance. So here if we solve it and square it for that, so it will be 9.33 into 10 raised to the power 4 whole square is equal to 1 by LC. Okay, and just a second. So C is equal to 1 by L V square P, which is 1 by L 3.65 into 10 raised to the power 3 into what is Vp? We just calculate whole square. If we solve it using the calculator, then the value will be come out to be, let me check it. Its value will be 0.0315 microfarad per kilometer. Okay, then the characteristic impedance will be ZC is equal to under root L by C. What is L? It is already given in the question. C we just calculated. If we solve it, it comes out to be 340.4 ohm. Okay, so the correct option will be because D is the correct option. God is going from 340. It will come in between. Now, next question, question number 11. In air, a lossless transmission line of length 60 centimeter with L is equal to 10 microhenry per meter, C 62.5 picofarad per meter is operated at 20 megahertz. Calculate electrical length or electrical path length. Options are 75 degree, B 60 degree, C zero point 0.6 pi E, and D 0.25 pi C. These are pi C. Okay. So we have to calculate this. So let me solve it for you because I don't think some of the people will solve it. So in a lossless transmission line, we know that electrical length, electrical length of the cable is equal to LE is equal to beta L. Okay, so here beta is equal to what? It is 2 pi by lambda. And what is 2 pi? What is lambda? Lambda is Vp by F. So 2 pi F by Vp. And we just calculated, we know that Vp is equal to 1 by under root LC. So here in this question, L is given, it is 10 microhenry per meter. C is equal to 62.5 picofarad per meter, and F is equal to 20 megahertz, and L is equal to 60 centimeter because it is given a transmission line of length L of 60 centimeter. So here, what we going to do? LE is equal to beta. What is beta? 2 pi into F. What is F? F is given 20 megahertz. 20 into 10 raised to the power 6 divided by Vp. Vp is 4 into 10 raised to the power 7. Okay, we can calculate Vp like this from 1 by LC. I have already calculated it for you. Into 60, 10 raised to the power minus 2 because we have to convert it into meters. So if we solve it, it will come out to be LE, which is the electrical path length. It will come out to be 3 pi by 5 C, which is equal to zero point 0.6 pi C. So from here we can see that the correct option will be C, 0 0.6 pi C. Now the next question is an overhead line is connected to a terminal apparatus terminal apparatus through a short length of single phase cable. The characteristic impedance is 320 and 140 ohm. A traveling a traveling wave of 160 kV magnitude originates in the OHL and travels toward the junction of cable. Calculate energy transmitted in the cable for 5.6 microsecond after the arrival of wave at the junction. So the options are A 360 minus 364, B 378 minus 382, C 397 minus 401, and D 419 minus 423. So basically you have to give me the answer. I will wait for a minute, then you can give me the answer. Okay, let me solve it for you. In the question, it is given that overhead line of connected to a terminal apparatus through a short length. So basically, ZOHL is 320 ohm and Z cable is 140 ohm. Okay? And E is 160 kV. So transmitted voltage ET is equal to how much? It is 2 times Z cable divided by ZOHL plus Z cable. So 2 into 140 into E also 160 divided by 140 plus 320. So it will be equal to 97.39 kV. Okay. Therefore, transmitted current IT is equal to, it will be ET divided by the cable impedance, which is 97.39 divided by 140. It will come out to be 0.696 kiloampere. because it is in kV. So therefore, now we have to calculate the energy. Energy transmitted in the cable during 5.6 microsecond. Okay, microsecond. What it will be? It will be E into I multiply by time. What is E? 97.39 multiplied by 0.696 into 5.6. So if you calculate it, it will come out to be 379.43 in joules. Okay, so from this we can say that which is the correct option, 379, and I think it will lie in this range. So B option is the correct option over here. Okay, so these are some of the questions which which helps you in understanding the problems. I hope so. And we are towards the end of the lecture. I hope you have get a better understanding what I'm trying to do, and understand how these questions can be solved. Okay, 37.9. Yeah, option B. Yes, yeah, option B ही लगाया मैंने. I have ticked the option B. 379.4. 379.4. Yeah, 4043, it can vary depending upon the calculation. Okay, it doesn't matter, but the option will be B. So with this, I end today's lecture. If you have any question, you can ask. Otherwise, we will meet again next week on Sunday. Okay. Thank you for all joining. And if you have any question, you can ask. Okay.